Welcome to the second lecture of EE311. In the previous lecture, we have made a comparison between analog and digital electronics. Why analog is important, we explain. And then we have seen that there are four types of amplifiers depending on input and output: voltage, current, transconductance, transresistance. And we have seen that the requirements for the input and output resistances vary in between them. So you have to choose the correct input and output resistance combination for the correct amplifier type. So now we will learn how to design amplifiers starting from single transistors amplifiers, the easiest one. So in fact, there are like 6 types of amplifiers, and 3 of them are coming from MOSFET types. And they are named as common source, common drain, and common gate. We will see them one by one. What does this common source means? How a MOSFET operates, we will remember, so on and so forth. But there's one more in here. In fact, like for the first one, we can say that common source with degeneration as a fourth type. These common source amplifiers are generally used as voltage amplifiers. Common drains are unity gain voltage buffers, and common gate is used for current amplification with unity gain. This is just like, this may not mean anything to you at this point, but as we analyze each circuit, you will understand it has some meaning. And similarly, the similar structures can be formed by using bipolar transistors again, by using common emitter, common collector, common base, and of course, common emitter with degeneration. And we can say the same thing from the bipolar ones. Let's start analyzing them one by one and see how they operate and why do we call some of them as voltage amplifiers, some of them as unity gain voltage buffers. So for a common source amplifier, the general structure is something like this. We have our source, voltage source, of course it's AC, and its internal resistance RS. Maybe we can make it a bit bigger so that you can see it easier. There's some capacitance. I will explain why do we need that capacitance. Some resistance. The transistor MOSFET. Negative voltage supply. Another capacitor in here. CS. DC current source for biasing. VDD, RD, CC2, the load resistance, RL, and V out. So this is a typical schematic for a common source amplifier. So as you see, we have a MOSFET in here, and MOSFETs are 3-terminal devices. We have drain, gate, and source. These two capacitors are this one and this one are called as coupling capacitors. This is also coupling, and the name is CC1. And this one is bypass capacitor. So the function of coupling capacitor, they separate DC and AC signals. How they separate? Because the capacitance impedance can be written as ZC is equal to 1 over J omega C. We generally choose this capacitance value as large, okay? So at small frequencies, let's say this is 1 over j 2 pi fc. So when you're operating at DC, if f is equal to 0, this ZC goes to infinity. It behaves like open circuit. So in DC, the equivalent circuit is just this one. RD, transistor is there. CS is open circuit. CC2 is open circuit. And we have just this simple, very simple DC circuit. So this is DC equivalent. But when you operate at moderate frequencies, or like, the frequencies of interest, mid-band frequencies. So here at mid-band, this pi fc term goes to infinity because you choose C as large as possible. F is like mid-band frequency. And because of that, ZC goes to 0 at mid-band frequencies. So in AC, they behave like short circuits. So when you take a look at an AC, let's draw the AC equivalent network. Then this source is connected to here, and then we have this term, and this node is grounded because CS is short. This node behaves like ground because I'm talking about AC, and this node will be like RL. So basically what this coupling and bypass capacitors does is they behave like short circuit at high frequency or mid-band frequencies when you want to have the gain. They behave like open circuit at DC frequency. And what is the advantage of this thing? So by this way, you separate DC and AC from each other. So your DC biasing will not be affected from AC operation. Any AC signal will not affect the DC biasing around the transistor. For example, take a look at this node. At DC, this capacitor is open circuit. Gate current of MOSFET is always 0, and because of this, this node is always at 0 volt. So DC bias does not change. This Vs cannot affect the DC bias. But when you're operating at AC, at high frequencies, then this thing behaves like short circuit, and the input signal is transferred to the gate. So it's like a filter. DC, AC sources are not going to affect your system. At AC, DC sources will not affect your system. So you separate these two components from each other very clearly. So what I'm trying to do is I want to have some gain from here to here, and I want to calculate the gain in here. So when you are doing the analysis, you analyze the circuit in 2 steps. First, you do the DC analysis. You use the DC equivalent circuit. Do not worry about the AC components. Find the operating region of the transistor. Find the small signal parameters of the circuit. Then, when you find them, now kill all the DC components. Start doing AC analysis. How do you do that? For DC analysis, you kill all the AC sources. What does this mean? Voltage sources short. Of course, AC voltage sources are short. AC current sources are open circuited. And open all the isolation and bypass capacitors. So when you do this in the previous circuit, when you open all the bypass and isolation capacitors, this is gone. You don't need to worry about this part. This is gone. This is gone. You don't need to worry about this part. And the circuit is simplified into this two resistor, one transistor network. So this is my DC equivalent circuit. For all DC analysis, I'm gonna deal with this structure. Before going further, let's review the MOS basics first. And I'm gonna show you a very short video to explain the MOS operation. So let's start with this video. Okay, so this video explains very briefly how a MOSFET operates, but we will do more, of course. We have to model it like in as a mathematical box. So MOSFET is, as the name implies, a metal oxide semiconductor device. That's why we call it as MOSFET. It has four terminals. Most of the time we use three of them. We ignore the bulk connection, but it has four terminals: source, gate, drain, and bulk. And unless otherwise stated, you can assume that bulk is connected to source for the MOSFETs mentioned in this class. So it's like this. It is like four terminal device: drain, gate, and source. There's bulk connection, but most of the time we show it like bulk and source shorted to each other, and we have drain, gate, and source, three terminal device. Gate oxide and body forms a capacitor, so this part behaves like a parallel plate capacitor. And as an insulator or dielectric, we are using silicon dioxide, which is a very good insulator. And this is the IC having like two different MOSFETs on the same silicon chip. So let's continue. So dimensioning, if you take a look at the cross section, you have the gate connection in here. So this is gate, let's say drain and source, and this is oxide. So this dimension is the transistor width. You don't need to memorize them. These are a bit more technical details, and if you take 413 class or 414, you will learn more about them. And this distance in here is known as transistor length. So when you are designing these transistors, you generally draw the top view on the computer screen. So this three-dimensional view is in fact equivalent to your design, because in general you don't have any control on the third dimension, the depth of this transistor, but you only control width and length. So you draw these circles and you draw these rectangles and squares to form the transistor. So when you draw this is your transistor width, and this is the transistor length. Why is that important? Because it is related with the technology. Maybe you heard, different technologies like 180 nanometer, 20 nanometer technology, 50 nanometer. What does that mean? That means, in fact, how small you can draw this length. Maybe 10 years ago or 20 years ago, when I was a grad student, we were designing transistors, and the technology was 3 micron, which means that the minimum transistor length is like 3 micron. By the way, a typical hair thickness is like 100 micron, so you can scale it. Like you can make the transistor like 3 micron. Maybe it's in, let's say, 1990s, we have 3 micron. But nowadays, in 2020s, people have 20 nanometer, even less. 1 nano is 10 to the power minus 9. 1 micro is 10 to the power minus 6. So what does this mean? As the technology improves, you can make these transistors much smaller. So what is the advantage? The first advantage is on the same silicon area, you can fit more transistors. So you can make much more complicated circuits. That's one advantage. The other advantage is as the physical dimensions decrease, the parasitics decrease significantly. So take a look at it. You have some capacitance in here. If you make this device smaller, the capacitance will be smaller. Or you have some routing line in here. It has some resistive loading. If you make it smaller, the resistive loading will be smaller. So at the end, because of this decrease in parasitics, these transistors start operate at much higher frequencies. Think about the computer technology. Like maybe 20 years ago, the largest frequency that your computer can work was like 100 megahertz. But nowadays, you can operate like at 3 gigahertz. So that's the main difference. If you make the transistors smaller by improvement in the technology, then you can open them at much higher frequency rates, or you can fit them in a much smaller area. You can make much more complicated CPUs or analog designs or whatever. So as a designer, on this transistor sizing, you only control transistor length and width. The other components like dielectric thickness, diffusion thickness in here, gate thickness, so on and so forth, you don't have any control, unfortunately, because the factory that's fabricating these devices define it. Anyway, these are some general knowledge slides. So this is the cross-sectional view of the silicon chip. So what you have is, of course, gate, drain, and source. Bulk connection is in here. So you connect the substrate to some potential. How do you do that? You are using P plus doping in here. You have the P substrate. Because, if you have a metal, one metal, let's say, and one, let's say, N or P type semiconductor, this forms a diode, a Schottky diode. So when you apply a potential in here, let's say 5 volt, you won't observe that 5 volt in here because of this diode operation. But when you have metal, P plus and P, because of the work functions and energy band diagrams, this thing doesn't behave like a diode. There's a good ohmic contact between metal and P plus, good ohmic contact between P plus and P. So when you apply 5 volt in here, you can observe that 5 volt in here. And that is why when you're having bulk connection, you use this P plus region, because P plus makes a good ohmic contact with P substrate. It makes good ohmic contact with the metal line in here. So when you apply some supply potential, it is directly transferred to the substrate, and you can observe the same supply potential in here. But when you take a look at the other components, as you see, on P substrate, you have N plus doping for source, N plus doping for drain. So this is like a diode in here. There's another diode in here. So you have two PN junction diodes in between. So what does this mean? Let's draw it like this. First of all, you have two diodes back to back. So without biasing, no current passes between drain and source. You have two back-to-back connected diodes. Both of them cannot be opened at the same time. The other thing is, one end of this diode is connected to the substrate. So you want to keep these diodes off during the operation. To be able to keep them off, you apply a very negative potential to the substrate, and you ensure that there is no leakage from drain to bulk. There is no leakage from source to bulk at the same time by keeping these two diodes off. So bulk connection, bulk potential should be chosen such that these two PN junction diodes are off all the time. So for that purpose, for N-channel transistor, you connect bulk to most negative supply, VSS, or to source of the transistor. Either of them works properly. Okay, so this is N-channel example for bulk connection. I'm not getting into the details of this thing. When it is required, I'm going to explain once more during the lecture, but basically what you should remember from here, a transistor, an N-channel transistor, has three terminals plus the bulk connection. And this bulk connection is used to ensure the substrate is properly biased such that there is no leakage from source to bulk or drain to bulk. For that purpose, you are going to either connect this node to the most negative supply, VSS, or you can connect it to the source because source is at lower potential than drain or gate. So it's going to work properly. For PMP, this will be source, drain, and gate. There's the bulk connection. Again, the same story, but since the substrate will be N-type and source and drain areas are P+, you need to do the reverse. You are going to connect bulk to the most positive supply or, again, to the source of the transistors. So this is the cross-section for CMOS, complementary metal oxide semiconductor. So this is again an extra knowledge, but I just wanted to see the cross-section of a standard MOSFET. So for NMOS, if you want to keep these two diodes off, for example, you connect this thing to here. Similarly, or the most negative potential, whichever you choose. But in this case, the directions are different. So for that purpose, you connect this node to either source or the most positive supply. A typical silicon wafer has a thickness of like 500 to 600 micron. It's like a CD. And all these dopings are happening at the top 15 micron. So this is just an exaggerated drawing, but these dopings, NVALs, P+, N+, are happening at the upper surface of this silicon disk. And NMOS transistors, you can see different drawings. This is an NMOS, drain, gate, source. This is also an NMOS, drain, gate, source. You can use like the fourth terminal as well, drain, gate, source, and bulk. This thing is mostly used in digital circuits. This notation is mostly used for digital circuits. In the scope of this course, we will follow this notation. For PMOS transistors, you can see such a notation: source, drain, and gate. Source, drain, gate. Or by using the fourth terminal, source, drain, bulk, and gate. Again, the same thing for digital. This is more common. For 311, we will use this notation. Let's remember the MOS operation curves very briefly. So for the typical notation, drain, gate, and source, this is NMOS, let's say. The operation is like this: N plus P substrate, oxide, polysilicon, this is gate, let's say this is drain, and this is source. So in initial operation, if you do not apply any gate potential, you have two back-to-back connected diodes. No current passes. But as you increase the gate potential, then you attract electrons in the P substrate to the channel surface because of the electric field shown in the previous video. And therefore, you start creating some channel. As you increase the potential, the channel thickness increases and increases. But until you get to that threshold point, no channel is there, and therefore no current passing between drain and source. But when you pass that threshold voltage, the channel is formed and the current starts flowing. If you go beyond that threshold voltage further, the channel thickness will increase, the channel resistance decrease, and because of that, you start getting more and more current. So if you want to draw VGS versus, or ID versus VGS, we will have such a characteristic. Let's say this is the threshold voltage. No current passes until you reach that threshold voltage because no channel is formed. So channel is formed when you reach the threshold potential. And after that, there is this curve. So as you keep increase the channel, the current increases more and more. Another important operation curve is ID versus VDS. Of course, in the previous drawing, we assumed that no drain voltage is applied in here, but as you start increasing drain potential, then the channel, the formed channel, will start getting tapered like this. And after a while, there will be some pinch off, and because of that, the current passing through drain to source is limited, and which is known as saturation. So you can review this material from 212, or we can review them in the recitation hours or online class lectures. But basically what happens is when VGS is less than the threshold voltage, we have cutoff. No current passes. ID is equal to 0 because there's no channel. Once you have some VGS larger than VTN, now VDS potential plays a critical role. So when VDS is larger than, so VDS is larger than VGS minus VTN, now we have saturation, and as you see, the current is saturated. Okay. When VDS is less than VGS minus VTN, there is a linear relation between output current and VDS potential. So in this linear region, this behaves like controlled resistor. By controlling the gate potential, you can control the channel resistance in here, and the drain current will change linearly with VDS. But when VDS voltage is quite large, then because of tapering, pinch-off occurs. The electron transfer from drain to source or source to drain, whatever, is limited, and then the saturation occurs. And of course, this is also related with VGS potential. As VGS increases, the saturation level increases. So let's stop in here. for this lecture, and in the next lecture, I will continue with further analysis of MOSFET.